Welcome to The Explainer. Today, we're going to dive into something that honestly feels a little bit like science fiction. An AI agent that can find and fix broken infrastructure completely by itself. We're going to break down how you can take a really complex problem and solve it with a surprisingly elegant solution. So, let's get into it. Let's start with a feeling I'm sure many of us have been there. It's 3 in the morning, your phone goes off, you drag yourself out of bed, you check the alert, and it's not some fascinating, complex bug in the code. Nope, it's a typo. A simple, frustrating infrastructure blunder. And that exact pain point is what we're tackling today.
But what if you didn't have to deal with that? I mean, really, what if an AI agent could just swoop in, figure out what's wrong, and fix it, all without you lifting a finger? We're about to look at a really powerful new pattern that could let you trade in all that manual kube control struggle for just a single simple chat prompt.
All right, so how do we actually pull this off? Well, the hero of our story is a concept you've probably been hearing a lot about lately, the LLM agent. Let's break down exactly what that means right here and see how it becomes our automated troubleshooter.
At its absolute core, an agent is really just a large language model. Like a GPT-4 or a Llama 3 that's been given a specific job to do. And it's put into a continuous loop to follow until that job is finished. The real magic, as you're about to see, is all in the details of that loop.
The entire behavior of the agent is driven by this fundamental engine. It's a super simple but powerful 3-step loop. First, it thinks. It analyzes the problem. Then it acts. It runs a command or uses a tool it has. And finally, it observes. It checks to see what happened. And that cycle just repeats and repeats until the task is complete.
Okay, but for an agent to actually do things, to perform that act step in the real world, it needs a special way to connect to its tools. And this brings us to the key enabler, what we're calling the secret sauce that makes this whole thing work.
And that secret sauce is called the Model Context Protocol, or MCP. This is the thing that takes a standard LLM from being just a chatbot that gives you text and turns it into a real actor that can interact with systems and execute commands. It's a game changer.
I think this is the perfect way to picture it. The MCP is the bridge that connects the agent's brain, that's the LLM's ability to reason and figure things out, to its hands, which are the actual tools that can manage a Kubernetes cluster or make an API call. It's the absolutely critical piece for taking real action.
So, to see if this all actually works, we need a really clear, simple test case. For that, we're going to use something called a minimum functionality test, or MFT. It's a task that's so basic that the system should be able to nail it every single time.
And our MFT? It's a total classic infrastructure blunder. A simple typo in a Docker image name. You can see it right there, nginx, instead of the correct nginx. It's a super common mistake, it's trivial for a person to fix, and it's the perfect way to see if our agent is really paying attention.
So here's a quick look at the tech stack that brings this all to life. It's actually a pretty straightforward setup. We've got LibreChat for the user interface, a model like GPT-4 is the brain, and then a custom server uses MCC to give the agent its Kubernetes tools. And the whole thing runs on a local Kubernetes cluster where we've put our intentionally broken app.
Okay, so the stage is set, the actors are in place. Now for the fun part. Let's get to the main event and watch exactly how this agent takes a broken system and makes it healthy, all on its own.
So our test kicks off with this broken deployment. You see that status? Image pullback off. If you've ever used Kubernetes, you know this one. It's basically the system yelling, "Hey, I'm trying to download this container image you told me to, but I can't find it," which of course is because of our little typo. This is the problem the agent has to solve.
So what can the agent do about it? Well, through that custom MCP server, it has a few specific tools in its tool belt. It knows how to patch a resource to make a change, it can apply a totally new configuration file, or it can pull logs from a pod to do some more digging. These are its hands for fixing the cluster. And what's really amazing is how simple it is to give the agent these tools. That little bit of code you see there, that @self.mcp.tools decorator, that's it. That one line is all it takes to register a function and make it a tool the LLM can use.
It just shows you how extensible this whole system is.
And there it is. Mission accomplished. After going through its think, act, observe loop, the agent correctly identified that the typo was the root cause of the problem. It then used its patch resource tool to fix the image name in the deployment. And just like that, the app is healthy. The status is running. But here is the most important part, the real kicker. That entire fix, from diagnosing the error to inspecting the config, identifying the typo, and patching the live deployment, was all kicked off by just one single instruction at the very beginning. All of that complex work triggered by one prompt.
Fixing a simple typo is just the beginning, but it proves the incredible potential of this whole pattern. And it leaves us with a really interesting question to think about. What other manual, repetitive, frustrating kubectl struggles that you deal with are now ready to be handed over to an AI agent? The possibilities are really, really exciting to think about.